Welcome to the sixth session. Welcome to the sixth session of this fourth module, wherein which we will be discussing the advantages and the disadvantages of the two types of vertical as well as the horizontal axis wind turbines, and we will also discuss a few of the performance characteristics of a turbines. Okay. Now, basically, this performance of any typical wind turbine is being designed to give the maximum power coefficient with the tip ratio has been estimated over a range of different speed ratios and pitching angles using blade element theory. Information is being given on the power, torque, and thrust development. Even on the nature of the flow over the blades also plays a vital role when we are talking about the performance of the turbines. Before we just proceed for the performance studies of the turbines, let me talk about the advantages of vertical axis wind turbines compared to the horizontal axis wind turbines. Now, as we know the principle of working of both, we can differentiate it that the vertical axis wind turbines are quieter uh, due to the less vibrations that it is generating. As I have already told you, since the blades have been placed in a horizontal axis in the space in the of the certain height, everything has to be balanced by this tower. So when it is rotating, a lot of vibrations will be generated, and it has to be well designed to balance that vibration. That is first thing. And the second thing is these high vibrations also encourages, also increases the sound or the noise that is being generated by the rotation of the blades. That is the reason why these vertical axis wind turbines are much quieter than the less and less vibrated vibration. It does not need a yaw control mechanism because it can produce electricity regardless of the direction of the wind is blowing. Now, there are two advantages over here. The first advantage is here. When compared to the horizontal axis, vertical axis can generate electricity or can rotate irrespective of the direction of the wind, whereas the horizontal one has to be tilted, it has to be yawed, or it has to be tilted in the direction against the direction of the wind which is been blowing. So based on this, what happens, in whichever the direction the wind is coming, the yaw mechanism has to tilt the axis of the rotors. That is the reason why. So whenever it is not required, since the vertical axis wind turbines can rotate irrespective of the direction, then no point of yaw mechanism is required. That is the major advantage, and then can produce energy even at a lower wind speed, whereas the horizontal wind turbines require minimum of 88 kilometers per hour or 2 meters per second of speed, and needs a cut-in speed of 12.6 kilometers per hour, whereas this requires very much less speed in order to start and generate the electricity. Slower blade speeds, because the blades are closer to the axis of the rotation, the energy transmission is not much of great concern. Okay, can be installed in urban environments also, and residential and commercial areas because they operate at low noise level. Okay, that is one advantage. The major advantage, they can also be used in urban places also because they are not so noisy in nature, more eye pleasing than other larger. I don't mind, actually our major aim is to generate electrical energy, and if you can take one of the major advantages, the horizontal wind turbines, they spoil more worth lands, whereas this doesn't take much area. That is one thing, and second thing is even it is more eye pleasing. He just means to say that it looks better appearance, better aesthetic compared to the horizontal axis wind turbines. Can be coated with colors and match buildings and surroundings, because the smaller turbines, it is easy to maintain also. It is easy for the maintenance also near the ground, near buildings. Vertical axis towers are much shorter than horizontal axis wind turbines. As we just told you, the horizontal axis will have a nominal of 100 feet. 100 feet is much larger. See, the second floor will always have around 30 to 40 or 50. So you just think double that, maybe around 6 stories of building it comes to. Okay, so the generator is generally mounted closer to the ground, so the crane is not needed for serving and maintenance and assembling. Actually, a few points are not mentioned here. So one of the thing is the generator and all the system will be always placed at the ground level in a vertical axis wind turbines. It makes it too easy for maintenance and repair. Even in case of any repair or maintenance, it can be done very easily. Whereas the horizontal, it needs a big trouble, and we have to take a risk to go there and repair it, and we have to maintain it. That is the first thing. And the second point of thing is, since since it is closer to the ground, and when it comes to the assembly, when we want to assemble the system and we have to place the tower and the blades and all those things, a crane and a lot of exercise, a lot of complication actions needs to be taken in order to assemble the horizontal axis wind turbines, whereas here it is not much compared to that horizontal axis wind turbines. Now what are the disadvantages? Whereas that is what you can ask me is, in spite of so much of advantage, why this vertical axis wind turbines are not much used in Indian scenario? It is only because the major disadvantages are they are less reliable compared to the horizontal axis wind turbines and less efficient at converting wind into electricity. They rotate, that is different one. Irrespective of the wind direction, they will rotate. But conversion of this rotational energy or wind energy into electrical energy is less compared to that. That is the point to be noted. Obviously, whenever we take some equipment or when we want to go for that, we always go with better efficient equipments, isn't it? So this VAWT offer suffer from dynamic stall of the blades as the angle of attack varies rapidly. So what do you mean by this angle effect? Angle of attack means if you have a blades like this, the wind which affects this blade will be different in different angles. Now if you have a say, for example, if you take this blade, the wind of attack may be like this, the wind attack may be like this, the wind attack may be like this, the wind attack may be like this, or wind attack may be like this. So the wind attack is a different one. Whereas what happens, though we have a yawing system for a horizontal axis turbines, we will tilt it according to the direction. So the what happens, the angle of attack, the wind which attacks to this, the angle of attacks will be almost the same. Will be almost the same like this. It comes and attacks like this. Whereas here it will be, if a wind turbine blade is like this for a vertical axis, it keeps varying, makes the design complicated and the life of the blades less. The life of the blades will be less for a vertical axis wind turbines because of the different varying angle of attack. Is it clear? And the blades of vertical axis wind turbines are fatigued and prone due to wide variations in applied forces during each rotation. So it is only my return. This is an extension conclusions or a disadvantages from the previous second point. Because the angle of attack is different one, what happens? It will be subjected to the variation in the load. That is what we call it as a fatigue load. It experiences more fatigue load compared to the other one, that is a horizontal one. Whenever it experiences more fatigue load, it will be more prone to the wide variations of the applied forces. Whenever the applied forces are varying rapidly for each rotation, it may undergo deformations. Once it undergoes deformation, it completely spoils the complete rotational systems. Is it clear? This can be overcome by use of composite materials and improvements in the designs, including the use of aerodynamic wing tips that cause the spreader wing connections to have a static load. The vertically oriented blades can twist and bend during each turn. This is what I just meant to say. Deform. They may experience deforming or twisting because it is rotating like this. When it is rotating like this, it may undergo some twisting or it may undergo a bending during each turn, shortening their usable lifetimes. The life of the blades will be reduced by this. That is the major disadvantage of this. Requires a power and a starting motor to start the Darius wind turbine. So it is only required is we need a starting motors are required to start it. Okay, I need a guide I need a guide wires to ensure the pole stays vertical so blade rotation is smooth. Guide wires are always required. Actually, in the previous class, I have always shown the guide wires have been connected for the blades in order to avoid it getting deformed, and they have to be interconnected. And there should be a smooth rotation. Blade rotation should be there. So that is the major disadvantage of this. Not as efficient as horizontal wind turbine. We have already discussed in the first point. It is only because the reliability on this is less. Okay, now let me come to the performance quotient of performance of this. Basically, this performance of a typical wind turbine is designed with the different ratios, and this can be come across with maybe a general wind turbine will always have 30 to 40% efficiency, and we can raise it up to 50%. At times in a peak wind, we can raise this to 50% efficiency. See, after all taking so much of concern and with well sophisticated designs, we can achieve. That means converting wind energy into electrical energy. It is restricted or it is been maximum of 50% times the peak wind. That is in terms of when there is a peak of wind speed is there. If that sounds low, actually remember the turbines were 100%. The wind could completely drop after going through the turbines. That is the reason for this. Exactly. Now even we know this maximum wind speed may vary up to 50 to 55 in general, 55 miles per hour. And if you consider the maximum turbines, a general turbine can have a power ratings ranging from 250 watts to 7 megawatts. An onshore wind turbine with a capacity of 2.5 to 3 megawatts, which can produce more than 6 million kilowatts in a year. Enough to supply actually to 5 or 50% efficiency is much good. So you just imagine 6 millions of kilowatts of hour it can produce it per year, a one in wind turbine, which is supply for sufficient enough for any household or domestic applications. In that context, if I want to study how this performance does vary with respect to few things, how we can generate this, how we can study this power of coefficient of performance, and let us talk about power coefficients or its an efficiency. The overall turbine system efficiency. The wind power industry often calls it as a power coefficient, or we also call it as an efficiency, which can be given by CP. The technical and product literature is now full of it, and the term CP, I mean the power coefficient, an indicator of tidal wind turbine system efficiency. It is nothing but a power efficiency, or we can also call it as total wind turbine system efficiency. The term of power coefficient is commonly used to designate the efficiency of the entire turbine power system. As shown in the expression below, it is generally defined as the ratio of the electrical power produced by the wind turbine to the wind. That is what it is nothing but power coefficient, or it may be an efficiency. What is the power that the wind is carrying, and then what is the electrical energy? What is the amount of electrical energy that we have generated for with respect to the wind energy which is available for us? So that ratio is nothing but uh, the power coefficient. That is what he designed. A ratio of electrical power, energy power produced by the wind turbine P out in the formula below divided by the PQ. That gives us the power coefficient. P out, power out by power input. That is the general formula for any efficiency. Okay, we can write this expression with Cp as a quotient multiplied by the pin. If we can, if we know the power coefficient at a specific wind speed, we can multiply it by P in as calculated by. So this is what the same thing. I have taken this P out and P in I have multiplied it so that I can find out what is output that we can achieve with the knowing the power coefficient. That's it. Now, if you take this total wind power, a function of wind speed cubed, that is rho a v cube. This is what we were discussing it. This is the power in. The total power wind flowing into a turbine is defined by the fairly simple wind power formula showing it to the right. The power into the turbine blades is a function of wind speed to the third power v times and v air density and the swept area of the turbine blades. What do you mean the swept area? If you have a blades like this, if you have a blades like this, whenever this rotates, when you have a blades like this, three blades are there, whenever this rotates like this, whenever it rotates like this, whatever the air that is being swept by this area is called as a swept area. Is it clear? So the swept area of the turbine blades, a simple conversion of the wind power formula is shown below. The symbol looks like the backwards as in the other one. Rho is often used to symbolize the density of the liquid or a gas. In this case, rho stands for the air density. That a capital letter A represents the blade swept area. Note that the most common horizontal axis wind turbines, the swept area can be determined by the formula for the area of a circle, which is pi times the blade diameter, that is pi d square by 4 divided by 4. That gives us an area. This is what I just told you. This is a swept area. This is nothing but a circular one. So what we will do is we will calculate it by pi d square by 4. Okay. Thus the power in is given by half into rho a v q. This is a tremendously of a higher importance. Based on this aerodynamic consideration, the windmill is being designed. Now, if you take any object, if you take any general object, an object in an airstream experiences a force F imparted from the airstream equivalent to two component forces acting in one perpendicular known as a drag force and the one lift force. One is which is acting lift force and the other one is a drag force. The magnitude of these forces depends upon the shape of the object, its orientation to the airstream and the airstream velocity. Lift is denoted by L and drag is denoted by D, and the force, the resultant force which will be act in the direction of F. V is the velocity and this orange color is the one which is an irregular shape. The magnitude of these forces, okay, fine then. Objects are designed to minimize drag force are designed as streamlined because the lines of flow around them flow smooth stream like lines, as in the aerofoil section. Now, I don't want to go much deeper. Actually, I just want to explain this figure more deeper than this. Actually, now you just take any regular shape. Now the wind is blowing, whether it may be a wind or it may be a water or it may be anything. If you consider now the air is coming with certain velocity, when it exerts, when it finds an obstacle for this. Now the wind is blowing like this, wind is blowing like this, and there is an obstacle like this. There is an obstacle like this. Whenever there is an obstacle like this, it experiences two forces. One force which acts perpendicularly, one force which acts perpendicularly, which we call it as the drag force, and one and lifts the force, one which is acting, that is the lift force, and one which is acting along the direction of the velocity, which we call it as a drag force. Okay, now this resultant, I'm so sorry, the one force which is acting perpendicular to the direction is called as a drag force, and the one which is acting along the direction, which we call it as a lift force. Now what happened, there exists a resultant. Because of the lift force and because of the drag force, there exists a resultant force which will be in these directions. So same thing, based on this shape of the object, this lift and drag forces vary. Now here you can see this drag force is more for the figure A, whereas the lift force is less because of the object shape. The same thing if you take a aerofoil structure, a fish-like structure, if you take this where the lift force is maximum and the drag force is minimum, and the resultant force will change according to the lift and drag force. Now my dear friends, anything anything which is experiencing the floating effects will always have this drag and lift force, whether it may be a bike, whether it may be your kite, whether it may be a kite or it may be a car or it may be an aeroplane or it may be anything, will experience this drag and lift forces that makes them to be in the air, and that is also making them to be on the ground level also. Now you can see our normal cars moves with 100 kilometers per hour, and this is one car. Say for example I have a car. Now I have a car which is moving with a velocity of 100 kilometers per hour or 200 kilometers per hour. If the same car, if I make this to move with the, I'm not changing any design of this, I'm not changing. Say the same thing, if I make this to move with 400 kilometers per hour, what happens? Soon it starts to move with 400 kilometers per hour, it will be like this. It will be uprooted. It will be uprooted like this. It will be lifted like this. It is the only thing. Now that is the reason why the aeroplanes, before they take off, they will always move with the maximum speed and then they will take off. The same car, if I make this to be groundwards, if you take a Ferrari one, it moves with 200, 250, 300 kilometers. Now the ground level, the air, I am not making the air to move much at the bottom of this and lift this like this. Now this is the lift and this is the drag force which is acting like this, and this is the lift force which is acting like this. That's okay. So that is the major intentions. Now, if you see this, now you will understand it better. The lift force acts perpendicular to the relative wind. The lift force always acts perpendicular to the velocity. Is it clear? So what happens when I take this? When I take this and move it, the air which comes over here, the lift force makes this to move upwards. The lift force makes this to move upwards, the air, and then it will be fallen down like this. Is that clear? So the lift force, maximum lift force makes it to move in this direction. Is that clear? So that is the reason why these aeroplanes will be always flying with a tilted. Now that is the reason the blades will be like this while takeoff. While landing, it will be like this. Is that clear? So what happens? The force of the lift is actually stronger than the force of the wind against the blade or the drag force. This is a beautiful point. You have to remember that the force which have been exerted by the lift force is much stronger than the force which have been exerted by this wind or a drag force. This drag force will be acting along the direction of the wind. Wind ಈ ತರ ಬರ್ತಾ ಇದ್ರೆ along the direction of the wind the drag force will act. Drag force is always which drags it backwards. See, I'll tell you a simple word. When wind is blowing like this, when the wind is blowing like this, there exist two components. One is along this direction and the one is along this direction, and there will be a resultant force like this. So one, the lift force makes this lift like this. Is it clear? The other force, which is a drag force which acts at the backward position, which makes this to pull this backwards, which drags it back, where one which makes it to move in perpendicular direction. So these are the two forces which are predominant, where out of these two forces, the drag force or the lift force is maximum and very strong, which acts in parallel with air flows. This allows the turbine blades to rotate or the turn at a speeds greater than could be achieved relying on the drag forces alone. Is it clear? Although there's some speed, wind turbines also use this drag force to produce energy. Most horizontal axis wind turbines are designed to minimize the drag force while maximize the lift force. That is the reason. One interesting thing is, even when you go for a swimming, swimmers will always do it like this. Why? Because why can't you go like this? No, the area which is available, we are just penetrating the wind to pass through our external surfaces. The wind to penetrate or the fluid to penetrate with our, that is the reason why even the fish, have you seen any fish something like this, a flat plate like this? Have you seen any fish like this? A fishes will be always designed like this, a small, a penetrate like this. So that is the reason why even the aeroplanes or it may be a ship, they have always made in order to minimize the lift force or the lift forces. Okay, now here when it comes to the turbine, we want to maximize the lift forces. We want to maximize the lift forces so that it will rotate faster. Is that clear? When you are designing an aeroplane or when you are designing that, we will take into this considerations. Is that clear? So even while designing the aeroplane blades, we always see to that there should be a maximum lift force, because so much of heavy has to be lifted up. When it is landing, the minimizing the lift forces and maximizing the drag forces. Is that clear? So that is varied. Okay. Even if you just imagine if the aeroplane shape at the front, if it is not a sharp like this, if it is a flat like this, it cannot resist, it cannot penetrate, it cannot move faster, it will resist more air. Is it clear? So that is the reason. Now you can see this wonderful figure where if you take this as an object, this is a blade. The blade width at this point is less, whereas the blade width at this point is more. Why it has been intentionally made like this is because if the wind is blowing over here, the angle of attack is like this. Angle of attack means the air which is being attacking in this particular direction. So that what happens, the lift force is perpendicular to the lift force or the drag force which has been going along the angle of attack. Now please be careful here my dear friends. Now this is an angle of attack where this is the blade speed which is moving in this direction. The lift force is always acting in a perpendicular direction. Okay, now this is a chord line. Chord line means a simple line which has been drawn in order to find out the mid portion of that blade. This is the lift force which makes this to move in this direction, and this is the drag force which makes this into the lift force which makes it to move in this direction, and drag force will make it to move in this direction. So this is how. Is it clear? Now there exists a rotational speeds that generates a rotational speeds. Is it clear? This is what a relatively wind. This is an angle of attack, and this is the blade speed, and this is the lift force. This is the direction of blade movement. This is called as a blade pitch. Is it clear? This is the beauty of this lift and drag forces, and this also tells us the aerodynamic things. Now this actually this the reason why, if you have a curvature places like this, if you imagine this is a ship or a dolphin or it may be an aeroplane, this is how the stream will be placed. at small angles relatively to the direction of the air stream. That is, when the angle of attack is small, the low pressure region is created on the downstream. And the downstream means, now this is the upstream and this is the downstream. The tail part in the first figure, the tail part, it tells us the downstream, and the front portion we call it as the upstream. If it is like this is called as an upstream, and it is going at the backward, this is called as a downstream. Is it clear? Now if you take this as, this is an upstream, it is going like this, it is going like this, at this bottom whatever it is happening, this is called as a downstream, where the drag force is predominant, whereas here the lift forces are predominant. This is the reason why they always make this plate. Even if you take the vehicles, why this angle is being made, in order to make the streamlines to move easily. In this situation, the faster the airflow, the lower the pressure. The faster the airflow, the lower the pressure. This is known as a Bernoulli's effect. Okay, the lift force thus acts as a suction or a pulling force on the object in a direction at right angles to the airflow. Now you can see this, the second figure, where the zone of a positive pressure and this is a zone of a negative pressure, that is a suction. This is a cord, as nothing but the length. This is a trailing edge and this is the leading edge. This is a leading edge and this is a trailing edge. So this makes a good understanding of this. What is this, even the Bernoulli's theorem? I don't go much deeper into the Bernoulli's theorem because it is open to the computer science and electronics people don't understand. Now if you take this object, if I throw this, how long this will be in air? As long as it possesses some velocity, it will be in air. Once its velocity decreases, it just falls down like this. Is it clear? Whenever, say for example, if the aeroplane is moving with certain velocity, if you suddenly stop it, the turbines rotate, and if it is not moving, what happens? Suddenly it falls down. That's it. That is what a Bernoulli's theorem. A simple understanding of a Bernoulli's theorem is, any object which will be in air, as long as it has a resistance, it has got some velocity, and it just falls down. You throw anything, you just throw a stone. How long it will be in air? How? As long as it possesses a higher velocity. Once the velocity drops down, it will just falls down to the ground because of the gravity. That is an idea behind of this. So this is a wonderful concept of aerodynamic system which experienced by the blades. That is the reason why you don't see any rectangular plates, or you don't see any cubical plates, or you don't see anything. You always see an upstream with a wider and a downstream with a minor trailing edges. It is only to make a minimum pressure regions. Minimum the pressure regions, the minimum the noise it does makes.